For this next lesson, we'll be focusing on the properties of exponential functions. Now, at this point, you've already kind of seen the curve of an exponential growth function and an exponential decay function. And the other benefit that you have is you've actually worked with other functions before, so you kind of have an idea of how functions work. So generally speaking here, in exponential functions, we have our parent function like we always do. In this case, y equals b to the x power being our parent function. Now, just your general stretching and compressing is done by the multiple that you multiply to the parent function, which in this case is the a that we've always been dealing with. And you can see here in this example number 1 how multiplying the base function to the x times 3 instead of 1 will actually make it a much steeper curve and have it rise more quickly. So you can also see that the y-intercept for y equals 2 to the x is 1, because it's technically what we're doing here is we're y equals 1 times 2 to the x power. And then the other one is y equals 3 times 2 to the x power. So the blue curve has a y-intercept of 3. So just some general information that you probably are comfortable with at this time if you know what the curve looks like. Now, as always, the h and the k for the translations will come in here at this point, and then you have the full transformation that can take place with the shrinking and compressing and the side-to-side and vertical translations. And so you can see here different combinations in this concept summary with the a, the h, and the k. And so hopefully this is something that you're comfortable with at this point in time. Now, I've given you quite a few examples to practice on. You're more than welcome to sketch those by hand. I'm going to simply demonstrate them on the calculator, and you can do the same thing if that's what you would like to do. So I'm going to go ahead and move over to the calculator to work on all of the sample graphing problems. Okay, so I'm going to just start with our parent function. I'm going to go ahead and enter our parent function so that we can see what that looks like, and we can have it as a means of comparison. So now I'm going to graph sample problem number 1, which is 2 raised to the x minus 4 power. If I hit enter there, you can see in general from the y-intercept we would move over 4 units to the right, and you would see that our new point is right there to the right. So generally this just shifted everything to the right, as you would suspect that it does. Okay? So now, just go ahead and delete that one. Okay, now I'll do sample problem 2. So sample problem 2 is going to be 2 raised to the x power. Now, when you're doing this in your calculator, you're going to need to make sure that you arrow out of the exponent. So when you subtract the 3, you're not subtracting the 3 from the exponent. And so you hit enter here, and you see that we drop down 3 places. And so now we had a y-intercept here at 1, and it dropped down 3 units to a negative 2. Now, the other thing that you got to keep in mind when graphing these things or identifying these graphs is if we have a vertical translation, the horizontal asymptote also is moved with the translation. So now the new asymptote would be y equals to negative 3. So you just need to be aware of that. Now we'll focus on sample problem number 3, which has multiple transformations going on in one particular graph. So we'll come in here and say 2 times, and this time the base function is not 2 to the x, but it's 3 raised to the x power. So we know that that's going to be a little steeper. And then we have vertical and horizontal translation going on here at the same time as well. So if we hit all of that in, so you can see here all the different parts that are taking place in the given transformation. And so everything is happening at one time. For sample problem number 4, if you look closely at this, you can tell that since we have a value between 0 and 1 as our parent function, we are now dealing with the decay value, and then we also have other transformations going on. We're making it steeper, and we also have vertical and horizontal translations, and so you can see how that would play out as well. So the next type of exponential function that we need to work with is with a function that actually has an irrational base as opposed to a rational base. So everything that we've dealt with up until this point has been with 2 to the x power or some other base to the x power. Now if you look here at this first little paragraph, you'll look and see an equation y equals 1 plus 1 over x raised to the x power. Now, what you may be thinking to yourself is that looks very similar to the compound interest formula, except you don't have the rate and a number of compounding periods, and you don't have a time with it, but it's very similar setup. Well, if you were to graph that particular function right there, what you would end up with is you would end up with an asymptote that is approximated at about 2.71828. That number is what we call the irrational number E. E is used in a lot of science and business calculations when we want to get a continuous growth or decay value. And so we tend to call E a natural base whenever we use it in exponential functions. And so this is going to be our next part that we're going to work with exponentially. And so in the previous lesson, we dealt with compound interest. Well, we can now use E to figure out a continuously compounded interest. So before we were talking about maybe doing it monthly, quarterly, daily, and we were breaking our annual interest up into those individual payment parts. Now, what we're basically going to be saying is that we are going to continuously put the interest right back into the account every second of every day. And so since we have computers, this is much easier to do. And if you look at this little summary box of comparison of a $10,000 investment account at 12%, you can see the different values that happen as a result of different compounding features. If you notice, with each increase in compounding all the way up to continuously compounded interest, that the jumps in the value become less and less, and they get closer and closer and closer. So you would think that the more you compounded something, the more it would jump up in value, and it actually has that reverse effect. It has that leveling off of the value. And so we can actually come up with a compound interest formula that is using the E as a natural base, and it's the continuous compound interest formula that you see right here. So now we're taking the principal and we're multiplying it times E raised to the R times T. So this is slightly different than the compound interest formula that we're using for continuous compounding. And so whenever you read a problem like sample problem number 5, you want to be very aware if it's asking you to compound monthly, daily, annually, or is it asking you to compound it continuously. And so once you see continuously, you'll know that you'll need to move to a different formula. So go ahead and try sample problem number 5 right now. This is something that you should be able to do pretty comfortably, and we'll look at that in just a second. Okay, so if we look at the problem here, we see that we have a beginning balance of $3,000, and so I'm just going to plug this into the formula. Our principal balance is $3,000. We have a base E. We're raising it to the R, the rate of 0.05 times the number of years, and it's asking us to do 4 years later. So that is my calculation that I need to put into my calculator. If we look at the problem where it asks us to round that to the nearest dollar, so we would simply say $3,664. And that's a pretty good straightforward problem to learn continuous compounding. All right, very good. So now that we've seen how continuous growth and decay functions can work within the context of compound interest, we have a lot more applications in using the irrational number E in science applications. Now, you can see here in this particular sample problem that we're using it for radioactive decay, the word decay model for carbon-14. And now we can see that the formula for radioactive decay is really the same formula as what we saw for continuous compounded interest, except we have this A to the O, the subscript O. Anytime you see a subscript with a 0 like that, all that's really saying is that it is the initial amount of whatever it is that we're looking for. And so in this particular case, if the amount of what it is that we're dealing with is carbon-14, A to the 0 subscript is the initial amount of carbon-14, and the A that we're looking for is the remaining amount of carbon-14 after the decay model has taken place. Now, if you notice in sample problem number 6, I'm going to let you do this in a second, the formula is 3.6 e to the RT, and you may be thinking to yourself, well, wait a minute, 3.6 does not create a decay model. That's a positive, that's values greater than 1, and so what it ends up doing is creating a growth model. But what you'll notice is right after that it says that the R is a negative 1.21 times 10 to the negative 4th, and so what you're going to have there is a negative exponent value that is actually going to create a fraction between 0 and 1, and that's where the decay is actually going to come from. So take a little time here for sample problem number 6 and actually read the whole scenario, read what's given to you, and see if you can apply that information and the formula at the top of the page to parts A, B, and C. Okay, so what we've got here is a formula, 3.6 e to the RT, with a rate. And that rate is written in scientific notation, and if you feel like you need to, you can go ahead and convert that to a decimal. You just work the decimal places backwards 4 places, and you're going to get like negative 0.000121, and you can use that in place of your calculation, but whatever way you need to do this. And so part A says, we'll find the amount of carbon-14 present initially after the kill. Well, at that point in time, 0 years have actually passed by. So we have a T of 0 initially after the kill. And so we have 3.6 E. And I'm just going to go ahead and put this in like the scientific notation. And of course, our time is 0. And anything raised to a 0 power is just 1. So we actually have 3.6 grams of carbon-14 initially present immediately after the kill. Now, part B says how much C14 is left after 9,833 years, and then we've clearly gotten to a fossilization at this point of the actual bone, and so we're going to say that T is equal to 9,833 years, and we're just going to have the exact same setup. 3.6 E, and then if you use your calculator effectively, you'll get an approximate value of 1.1 grams of carbon-14 remaining in the fossil. So this is a good use of the formula that we have here for continuous decay. Now it asks us to graph the model. Now the key here is really getting the scaling correct, and so I'm going to go ahead and set that up right now. Okay, and so you can see here for grams, I just used a single number, 1, 2, 3, 4, 5 grams. But for the time function, I actually used 5, 10, 15, 20, but representing the number of thousands of years that have passed by. Now, if you feel like you need to t-chart more points, that's perfectly acceptable. I've got 2 solid points from parts A and part B. So if I go to t equals 0, I'm at 3.6, and so that's our y-intercept. And if I go to 9,833 years, which is close enough for me to approximate to 10 years, that's going to be about 1.1 grams, and so I can approximate that. And I know that we're working with an asymptote, and so that would be a pretty good generic graph or sketch of this model. So, all right. There's a good application problem for continuous decay in reference to a science application.